we saw differentiating the exponentials, so let's go back the other way. How do we integrate them? Just like we saw with differentiation, it was relatively easy. It all came down with the power of the function. At this stage, it's the same when we're integrating. If it happens to be a linear function, I personally find this, what they call standard integral, a bit limiting, because the power has to be a limiting function, a linear function. So if it happens to be a linear function, then when we integrate it, we get 1 over the coefficient of x, e to the ax. I find it more useful to think of it like this, because we know that when we differentiate, we'd like the derivative times e to the function x. So we want to create that. And so the way I think about it is, if I'm just going to simply integrate an exponential function, I would like to see the derivative in front of it, and I'm going to try and create that. And if I can create it, then I know that it must have come from e to the function x. Because when we differentiate e to the function x, you get f dash x e to the function x. That is fine as long as when we manipulate it, all we're doing is multiplying or dividing by a constant number. If we have to multiply or divide by pronumerals, then we'll end up using a technique that we'll look at later in four-unit integration. But you won't ever see ones like that in 3 and that, unless they give you big hints on how to do it. So okay, at this stage we'll be limited to fairly simple ones. So here's e to the 5x. Yes, it is a linear function, so I can go, oh, well, 1 over the coefficient of x, that would have been 1/5 e to the 5x. But what I'm getting at is, the way I probably think about it is to go, well, e to the 5x, gee, what I really would have liked to have had there was 5e to the 5x. I'd like the derivative out the front. Can't just change the question, of course. So to balance it out, I put the 5th out the front, and then I know the 5e to the 5x gets e to the 5x. We get the same answer. You'll probably get into the habit of working both ways. I mean, once you see it's a linear function, if you're a linear function, 1 over the coefficient of x probably is quicker. But for other types, all right, I want to try and create the derivative. So this is what I mean, x e to the x squared. It's not a linear function, but I can create the derivative by simply multiplying or dividing by a constant. The derivative would be 2x. So if I change that to be a half of 2x e to the x squared, then I know the 2x e to the x squared, that must have come from e to the x squared. So that's a half e to the x squared. 9x minus 5, again, linear function, so I could, although I didn't in this case, but I could have just said 1/9. But using the derivative idea, okay, what I'd like would be 9e to the 9x minus 5, balance it out, I want a 9th out the front, and it becomes, there we go, 1/9 e to the 9x minus 5. So that's what I mean. If you remember that idea about linear functions, it is going to be quicker to go, oh, it's just 1 over the coefficient of x. You can get straight from there to the answer. But otherwise, you're thinking about, hey, I want to create the derivative. Now, things like this, the square root of e to the x, remember we don't have rules for how do you differentiate the square root of something. So we're going to have to put it into index form. That would be e to the x on 2 or a half x. Again, that is a linear function, so I could just say 1 over half. But I'm going the other way. I want to create the derivative, which is a half, balance it out. I've got 2 out the front. And so we get 2e to the x on 2. Look, I'm always in the habit of rewriting it the way the question's asked. So they asked it the square root of e to the x, and my answer I've got square root of the x. Reality is, I mean, that second last line is an answer. But I just tend to write my final answer however they've given the question, that's format. Okay, we don't have a product rule, so before I do this one I'm going to have to expand out and then each individual term. So the e to the 2x, fortunately they're all linear functions, so I can go half e to the 2x. E to the x is just e to the x, and the 3 of course becomes 3x. We don't have a quotient rule. Mind you, it would be silly to use a quotient rule for this one anyway, because we can just use our index laws and tidy that fraction up. Divide everything by e to the 2x. Well, the e to the 5x is divided by e to the 2x, e to the 3x. minus e to the minus x. Be careful with our negatives here, because yes, they're linear functions. A third, but minus becomes plus, so we've got plus e to the minus x when we integrate that one. Remember, if ever you're unsure about your answer, you can always check, of course, because all you do is differentiate your answer and you should get back to the original question. Let's do a definite one. Okay, not a linear function, but you'll notice we've got x squared out the front, so we can create one by just multiplying by 3. But if I multiply 3, I've got to divide by 3. The 3x squared e to the x cubed must have come from e to the x cubed. Sub in 1, sub in 0. E to the power of 0 is, of course, 1. And so there's our answer, 1/3 e minus 1. What if the base is not e? Well, we saw when we differentiated, we fixed that up by simply multiplying by the natural log of the base. If we're going back the other way, then logically, to fix it up, we would divide by the natural log of the base. So we still do it as normal. 3 to the x goes to 3 to the x, but we'll divide by the natural log of the base. Okay, that shall do us.